All right. This is 2007 number 3 E&M. Diagram above, nichrome wire of resistance per unit length lambda is bent at P and Q to form a horizontal conducting rails that are a distance L apart. The wire is placed within a uniform magnetic field of B, pointing into the page, a conductive rod of negligible resistance, which was aligned with end PQ at time equals 0, slides to the right with constant speed V, and negligible friction. Express all algebraic answers in terms of given quantities and fundamental constants. Indicate the direction of the current in the circuit. So we have an induced current because we are moving our rod to the right? That is increasing the amount of magnetic field in this loop right here. Right, as that loop gets bigger, we're going to get more magnetic field into the page. The current in the wire is going to act to oppose that. So if we're getting more magnetic field into the page, the induced current is going to want to create field out of the page in order to oppose that increase into the page current. So if we are creating current that is out of the page, and we curl our fingers using the right hand rule, means that the current has to go counterclockwise. Counterclockwise current will create magnetic field out of the page to oppose the increasing magnetic field into the page. Next. That's basically what I explained here. As the rod moves right, amount of magnetic field in the page increases. To oppose that, the current is induced to create field out of the page. Right hand rule gives us the necessary direction of the current. Clockwise, counterclockwise. Derive an expression for the magnitude of the induced current as a function of time. So I've got a couple different things going on here. First, we have these two equations. All right. We're looking for current, right? And in order to find current, we're going to need to know what the induced EMF is going to be, right? Induced EMF comes from this equation, right? Where the induced EMF is the change in flux over time, right? D flux dt. So we got to solve that equation first. There's a couple things we can do here. First is realizing that flux is equal to the magnetic field times the area. If we take that to a partial, right, it's going to be a tiny amount of flux in a tiny amount of area. We can substitute that in for d flux, right, a tiny amount of flux. So B dA gets substituted in for d psi? I forget what that Greek letter is. Flux. So we substitute B dA in for that over T. dA, we can substitute in with L times dx. Dx being a tiny amount of width right here, right? So dx, L being the length or the width, whatever you want to call it, between the wires there. So we can split that into our little area into L times dx. So we can plug that in there and we end up with dx over dt, which we know is velocity, right? Dx dt is velocity. So our induced EMF is going to be V times, this should be capital L, times V. All right, so we figure out our induced EMF. We can now plug that back in up here. So we get I times R is equal to BLV. We rearrange for I. Problem is R is not a given constant or a given value or a fundamental constant. So we have to figure out what the resistance of the loop is equal to. They give us the resistance per unit length as lambda. So if we can multiply lambda by the total length of the wire, which if we look at this up here, right, the length of the wire is going to be here to here to here, right? This section right here. The rod doesn't have a resistance. It says that it's negligible resistance. So it's just these three sides. So L for sure is part of the length. And this distance here, I'm going to call it X, right? We already used X for these little distances. So we'll get lambda times L plus 2X, will give us the resistance. Again, x is not a given variable for us to work with, but if we use our velocity equation, velocity is equal to distance divided by time. Distance multiply time up to the other side, we'll get distance is equal to the velocity times time. Velocity and time are both things that are okay, right? Because we want this as a function of time. So we can plug that in there. So we replace r, which was not allowed, with lambda times L plus 2vt, which are all things that are allowed, and we get our current equation. Derive an expression for the magnitude of the magnetic force. Magnetic force is ILB, current times the length times the length of the rod times the magnetic field. So we can just do that really quick. We just substitute in BLV over lambda times L plus 2VT for I multiplied by LB. We multiply those through, we get B squared L squared V over lambda times L plus 2VT. On the axis below, sketch a graph of the external force as a function of time that must be applied to the rod to keep it moving at a constant speed. So the one thing to kind of recognize here is that the external force has to be equal and opposite to the magnetic force, which we just solved for right here. So external force is going to be equal to the magnetic force if we are going to keep our object moving at a constant speed. So if we put time is 0, right, because it says to label the values of the intercepts. So we do have an intercept here at time equals 0. When time equals 0, this goes in as a 0. This goes away, leaves us with lambda times L. There's already an L on top, so the L cancels with L squared, and we end up with B squared L V over lambda as the starting external force. And then as T increases, this is going to go towards 0, right? Because T is going to get bigger and bigger and bigger. It won't ever reach 0. It's an asymptote. So we come down to an asymptote at 0 for the external force. And there is our graph. The force pulling the rod is now removed. Indicate whether the speed of the rod increases, decreases, or remains the same. Speed has to decrease. If you remove that external force, the only force acting on the rod is our magnetic force. Magnetic force, if we check up here, if we use our right hand rule, right, velocity this way, magnetic field, no, we want the current. It's the current that's causing the force, right? So the current is counterclockwise. So current is up, magnetic field is in. We can look at the direction of our thumb. Our thumb is pointing to the right. So the magnetic field or the magnetic force is to the right, opposing the motion of our rod. So if we take away the external force that's pulling our rod to the right, we're left with just the magnetic force, which is pulling our rod to the left in the opposite direction of velocity. That's going to leave us with a negative acceleration, or acceleration to, I guess, it's going to be to the left. Negative acceleration or left acceleration with a positive or right velocity will lead to our object or our rod slowing down. And it'll slow down until it stops moving, and then the current will drop to 0, and we won't have any induced force or anything like that. So there is number 3. Way, way better than number 2, for sure.